So far, we have learned about point estimators. For example, the sample average is a point estimator of the population expectation. Point estimators, when you are given a sample, when you calculate the point estimator, it's going to yield a number. That number may or may not be close to the true parameter value. And with only that number, we can say relatively little about the parameter. It usually leaves much information to be desired. For example, a political poll estimates that 49% of Wisconsin voters will vote for Trump and 48% will vote for Biden. And the question that you really want to answer is who will win Wisconsin? Let's suppose that the poll included a random sample, an IID sample of the Wisconsin voter population. So we abstract away from sample selection. Let's also disregard all those complications caused by voter turnout or electoral college. But even then, even when we rule out all of those complications, there is still the question of how much the poll numbers tell us. The poll numbers, these numbers are realizations of vote share estimators based on a sample from the population. If we know the sample size, then we should be able to calculate the standard error of the vote share estimators, and we can also obtain an asymptotic distribution of the vote share estimators. And that will be a lot of information, and those are very useful. So asymptotic distribution and standard error are very useful tools to assess the accuracy of the estimators. But standard error and asymptotic distributions are not very straightforward to understand, to describe. There is an easy way to describe the accuracy of the estimator. That is, to present the information contained in the asymptotic distribution. And this easy way to present the information contained in the asymptotic distribution is confidence interval. So what is a confidence interval? A confidence interval is a random interval. So it's important to realize it is an interval, but it's a random interval with a confidence level attached to it. So it's a random interval with a confidence level attached to it. For example, if this interval Ln to Un is a 95% confidence interval of mu, what we are saying is probability that mu belonging to this interval is 95%. So here the interval itself is random. Ln and Un are random. These are random variables, and they are functions of the data. And such a random interval is a confidence interval with a confidence level given by a probability, for example, 95%, if the probability that this interval include the true value equals that probability, 95%. The random interval like this is also called an interval estimator. So it is also an estimator. It is also a guess of the true parameter. But the guess is not a point guess, but rather an interval guess. So the guess is that the true value is in this interval. So the random interval, the confidence interval is an interval estimator. As I just said, the endpoints of the interval are random, L and UN are random. They are functions of the data. And the value that they are intended to cover is the parameter. The parameter is non-random. So the interval is random. The interval estimator is random. True value is not random. So when you are trying to understand what we mean by probability mu belonging to this interval, that probability is taken with respect to the randomness in LU and UN, LN and UN, not with respect to randomness in mu, because there is no randomness in mu. So that should be LN. So the event mu belonging to Ln UN is equivalent, can be equivalently written as the random variable Ln. That should be Ln. Is less than mu, and the random variable UN is greater than or equal to mu. So that event is the intersection of these two events. And these events are about the random variables Ln and Un. So the random confidence interval is an interval estimator, and it is a random interval. But that's one thing to that I want to emphasize about confidence interval. The other thing is that the random interval should have the desired confidence level. It has a confidence level attached to it. So we want to choose this Ln and Un so that the probability of this event is equal to the desired confidence level. As we will see later, that typically we will not be able to make the probability of coverage to be exactly equal to the confidence level, because we typically do not know the exact distribution of Ln and Un. Usually we're going to use asymptotic distribution, and we will try to make this coverage probability to be approximately equal to the desired confidence level. So let's see how we do this. If we don't put any other restriction on the random interval, on the Ln Un, we are not able to pin down one interval that satisfies this equation. If we don't put any restriction on Ln Un, then there are many solutions to this equation. Why a simple way to see that is to see that this is one equation, and we are trying to figure out two quantities. Clearly, the answer is not going to be unique. There will be multiple answers. However, conventionally, we assume symmetry. Conventionally, we're going to assume symmetry. So what does symmetry mean here? Symmetry means that this interval is centered at the parameter estimator, the point estimator. That is, the interval is symmetric around the point estimator. Well, that makes sense because the point estimator is our point guess of the population parameter value. Our interval guess is reasonable to require that the interval guess to be an interval around this point guess. So conventionally, we impose symmetry when we do impose symmetry, then Ln will be the point estimator minus half of the length, and Un will be point estimator plus half of the length. And half of the length of the interval is denoted by Dn. So if we impose symmetry, then Ln and Un will be this form, will be related to the point estimator in this way. And now all we need to figure out is this one quantity, Dn. We want to figure out what Dn is, what Dn should be, to make sure that our confidence interval has the right coverage probability approximately in large samples. So how do we do that? So we start with the coverage probability itself. So this is the coverage probability. On the previous page, we demonstrated that this is probability that mu is belonging to Ln and Ln to Un interval. So this event indicates coverage. So the interval covering the true value. So we start with the coverage probability itself. And we look at these two inequalities, these two events. Now, suppose for each of the inequality, I move mu to the left-hand side, I move Dn to the right-hand side. Then I'm going to get the difference between xn bar and mu being less than or equal to Dn. So this inequality is equivalent to this one. And similarly, we also turn this into this equivalent representation. We move mu to the left-hand side and Dn to the right-hand side. We get xn minus mu being greater than or equal to minus Dn. The reason we want to bring mu together with xn bar is that this difference is something that we can apply the central limit theorem on, so that we can figure out the distribution of this quantity. So to apply the central limit theorem, we also want to bring it even closer to the form that the central limit theorem has something to say about. So I multiply square root n minus mu by, I multiply xn bar minus mu by square root n. Multiply square root n to both sides of the equation. And now I can also divide both sides by sigma, the standard deviation of the data, standard deviation of the population. So I divided by the standard deviation. What I obtain is this last line. So this recentered and rescaled sample average is less than or equal to root n dn divided by sigma, and greater than or equal to negative of that. So we turned this coverage probability into a probability about this random variable. For this random variable, even though in general we do not know its distribution, but by central limit theorem, we know it is approximately standard normal. So this is approximately standard normal at large sample size, at large n. So that is approximately standard normal. That means this probability is, so this probability, which is copied here, this probability is approximately the probability that a standard normal random variable being less than or equal to root n dn over sigma and greater than or equal to negative of that. So it equals the coverage probability of that interval is approximately the probability that the standard normal falls between these 2 points. And so what is the probability that the standard normal falls in between this point? We can look at this standard normal probability density function. We know that it is symmetric. So the probability that the standard normal is between 0 and the positive value square root n dn over sigma is the same as the probability that the standard normal is between minus square root n dn over sigma and 0. So these two parts have equal probability due to the symmetry of standard normal. Therefore, this probability equals 2 times this probability. 2 times this probability, right? 2 times the probability that the standard normal is in between 0 and square root n dn sigma. So that equals, so I'm going to skip this line, and that should equal 2 times probability that standard normal is greater than 0 and less than or equal to root n gn over sigma. So I want that to be 95%. I want that to be 95%. That means the probability that standard normal is between 0 and root n dn over sigma is half of 95%, which would be 0.475. So how to figure out root n dn over sigma? We can look at this standard normal table and look for the z value that corresponds to the probability 0.478. So which probability in the table is the closest to 0.478? So we look it around and we found it is here. That probability is exactly 0.475. And that 0.475 corresponds to the z that is 1.96. So that corresponds to the z value that is 1.96 in this table. So therefore, root n dn over sigma should be 1.96. If root n dn over sigma is 1.96, then this probability is 95%, and the coverage probability of our confidence interval is approximately 95%. So if sigma is known, then we can figure out dn very easily. Dn will just be 1.96 times sigma divided by square root of the sample size. And that is how you figure out the confidence interval, the symmetric confidence interval, in the case where sigma is known, the standard deviation of the population is known. So the confidence interval is, so the CI, confidence interval CI of 95% is xn bar minus dn 1.96 sigma divided by root n, and xn bar plus 1.96 sigma divided by root n. So that will be the symmetric 95% confidence interval of confidence level 95%. Now let's continue assuming that sigma is known and try to figure out, try to consider other confidence levels besides 95%. So sometimes 95% is a very commonly used confidence level for confidence intervals. But other confidence levels have been used also. In general, the confidence level is denoted by, in general, this is denoted by 1 minus alpha, where alpha is a probability. So it's between 0 and 1. So typically alpha is a smaller probability, it's between 0 and 1/2. In principle, it can be between 0 and 1, but if alpha is close to 1, then you're looking at a confidence interval of a very low confidence level, and that wouldn't be very useful. So typically alpha is between 0 and 0.5. And the confidence level is 1 minus alpha. You might wonder why we use 1 minus alpha, not alpha, to denote the confidence level. And well, that's just a convention. The convention is to let alpha denote this smaller number, while use 1 minus alpha to denote the confidence level for the confidence interval. So if we want a confidence interval that is of confidence level 1 minus alpha, then we will want, from the previous page, we'll see that we will want this probability. I can copy that formula. We want this probability to be equal to 1 minus alpha, or approximately equal to be equal to 1 minus alpha, because this is the standard normal already. And if this probability is equal to 1 minus alpha, then the coverage probability of our confidence interval will be approximately 1 minus alpha. So we want this to be 1 minus alpha. So how do we then decide, how do we find the desired value for root n dn sigma in this general case? So in general, what we are going to do is to write this probability as as 1 minus 2 times 1 minus the CDF of standard normal evaluated at root n dn over sigma. Here, this phi is the CDF of standard normal. So why does this why does this equation hold? Why does this probability equal to this? Well, we can draw a picture of the standard normal distribution. So let's say this is 0. We can draw this standard normal distribution like this. It's symmetric around 0. And let's say this is root n dn over sigma. And the mirror image of that is minus root n dn over sigma. Then the probability we want is the probability that standard normal is in between these two values. So we want this area underneath the standard normal PDF. But we know the total area underneath of the PDF is 1, right? Because PDF has to integrate up to 1. Therefore, the probability that we want is 1 minus the probability of this small tail area plus this small tail area. So if we exclude these two small tail areas, we're going to get the area that we desire. So what that says is that should be equal to 1 minus probability that normal 0, 1 is either greater than the positive or less than or equal to the negative. So that means the absolute value is greater than the positive. But now, what is the probability of the tails? Because of the symmetry of the standard normal distribution, these two tails are the same. Therefore, the probability that standard normal is beyond this point is equal to the probability that it is beyond this point. Because this area is symmetric to this area, and the PDF is symmetric around 0 as well. So therefore, the probability that standard normal is greater than this positive number equals the probability that it is less than this negative number. Therefore, the sum of the two probabilities will be 2 times one of them. Right? So therefore that probability equals 2 times probability that standard normal is greater than this positive number. So 2 times this part in green. But now, what is this green area? It is nothing but 1 minus the CDF of standard normal evaluated at this point. Why? Because the CDF evaluated at this point is the probability that the standard normal random variable is less than or equal to that point. And this little area is the probability that standard normal is greater than or equal to that point. The two probabilities add up to 1, therefore, the probability in this little tail area is 1 minus the CDF. So that probability is 1 minus probability that normal 0, 1 is less than or equal to root n dn over sigma. And that is exactly what I wrote down here. So it's 1 minus 2 times the tail probability, the right tail probability, and the right tail probability is 1 minus the CDF. I want to equate that to be to 1 minus alpha so that I can solve for this quantity. So now let's do that. Let's solve for this quantity. So I want to use this equation to solve for root n dn sigma. Solving this equation is quite easy. 1 minus this should be equal to 1 minus alpha. Therefore, 2 times this 1 minus CDF should be equal to alpha. Or alternatively, 1 minus this should be equal to alpha over 2. So that implies 1 minus phi root n dn over sigma should be equal to alpha over 2. Or in other words, phi of root n dn over sigma should be equal to 1 minus alpha over 2. Or in other words, root n dn over sigma should be equal to the inverse of the standard normal CDF. The standard normal has positive density everywhere. The probability density function is the derivative of the CDF. If the derivative is positive everywhere, that means the CDF is strictly increasing everywhere. So when the CDF is strictly increasing, it has an inverse function. It's invertible. Therefore, this equation can be solved this way. So root n dn over sigma should be the standard normal CDF inverse 1 minus alpha over 2. And this quantity has a name called the z-score. The z-score for the standard normal distribution. So the z-score denoted by little z, so lowercase letter z. I read it smaller, so you're not confused. So this lowercase z subscript alpha over 2 is defined to be standard normal CDF inverse 1 minus alpha over 2. In words, this is the 1 minus alpha over 2 quantile of the standard normal distribution. So that z-score is defined to be this inverse, and it is the 1 minus alpha over 2 quantile of the standard normal distribution. Using this z-score notation, we find that dn should be sigma over square root n times the z-score. So if you want the confidence interval, the symmetric confidence interval to have a coverage close to 1 minus alpha, then you will want dn to be equal to sigma over root n times the z-score at alpha over 2. So that is what the z-score means. So we have talked about the case where sigma square is known, but in general, sigma square is unknown. So sigma square is typically unknown. Sigma square may be unknown, but we have already introduced a consistent estimator for sigma squared. In fact, we have introduced two consistent estimators of it, but we can just consider one of them. We can consider this one. The other one just works as well. We can consider this estimator for sigma squared. The estimator is a consistent estimator, which we have proved already. But does that mean root n, when you replace the sigma by the estimator, this ratio is still asymptotically standard normal? Does replacing an unknown sigma by a consistent estimator preserve the asymptotic distribution of this ratio? The answer is yes. And it is by the continuous mapping theorem. Continuous mapping theorem. And the continuous mapping theorem is as follows. So we're going to talk about this continuous mapping theorem right now. So what is this continuous mapping theorem? It says that it considers the scenario where you have two sequences of random variables. Z1 and Z2n both are sequences of random variables. And suppose the first sequence converges in distribution to another random variable Z1. So Z1 is typically a random variable. And Z2n converges in probability to Z2, to little z2, where this little z2 is a constant. It's a non-random number. When Z1n converges in distribution to a random variable Z1, Z2n converges in probability to a constant Z2. And consider a function g that is continuous in both of its arguments at all the points Z1, Z2, where Z1 is maybe any value that the Z1 random variable can take, and this Z2 is this constant value. So this Z2 doesn't have to be any other value. It you only need to consider this value. If the g function is continuous at such points, then g of Z1 and Z2n converges in distribution to g of Z1 and little z2. So this is one version of the continuous mapping theorem, sometimes also called the generalized Slutsky theorem. So it says that the continuous function preserves convergence in distribution. Even if you have a sequence that converges in probability, it still preserves. So the convergence still preserves. So the statement of the theorem I'm giving here is sufficient for today's discussion. Here the Z1n and Z2n are two sequences of random variables. But in general case, this continuous mapping theorem holds when Z1n is a random vector, sequence of random vectors, and Z2n is also a sequence of random vectors. So in general, this holds when these are random vectors as well. And in the random vector case, convergence in distribution means a joint convergence in distribution, means that the joint CDF of this whole random vector converges to the joint CDF of this random vector. And joint convergence in probability means also the joint convergence, but it's equivalent to just element-wise convergence. So convergence in probability of a random vector to a constant simply means that each element of this random vector converges to the corresponding element of this constant vector. So when z1n and z2n are random vectors, z1n is of the same dimension as z1 is of the same dimension of the same length as z1n, and little z2 is of the same length as big z2, the big z2n. So I just want to mention that because, later on when we need this, I will repeat. But for today, we only need the z1n and z2n to be scalar random variables. So for today, what we want to study is this root n xn bar minus mu divided by sigma hat. So we want to study whether replacing the sigma by sigma hat by a consistent estimator still give us the convergence in distribution to standard normal, okay? It does because this ratio equals the ratio with the known sigma, with the true sigma, times the true sigma divided by sigma hat. So if you call these z1n, so if this you call this z1n, so that is z1n. And if you call this z2n, then g of z1n, z2n equals sigma z1n divided by z2n. This function, g of little x1, little x2 being sigma little x1 divided by little x2, this function is continuous in x1, very clearly in x1 at any value of x1. So it's not a question that is continuous in the first argument at any point, at any value that z1n can take. It is also continuous in x2 whenever x2 is not 0. It's also continuous in the second argument at any non-zero point. For the continuous mapping theorem, we only need the continuity of g in the second argument for at the value that the second argument equals the limit. That's the little z2, right? So this is continuous. And the second argument equals sigma. Because sigma is the standard deviation of the population. And for the population, we always assume that it has positive variance, therefore positive standard deviation. So it's continuous at the second argument at the point sigma. And therefore, the g function, the continuity of the g function, so it's also continuous in this first argument at all values. So therefore, this g function, the continuity of the g function satisfies the requirement of the central of the continuous mapping theorem. Thus, by the central limit theorem, by the continuous mapping theorem, g of z1n, z2n which is the quantity we are interested in, converges in distribution to G of Z1 and little z2, where Z1 is a standard normal and little z2 is sigma. So that equals sigma divided by sigma times a standard normal. That is a standard normal random variable. Okay, so by the continuous mapping theorem, this quantity with the estimated standard deviation is still asymptotically standard normal. So replacing the unknown sigma by its estimator doesn't affect our calculation of the confidence interval. Now let's consider an example. Suppose that a poll of 100 people shows that the support rate of the president is 40%. Now we know the sample size of the poll, which is 100, n equals 100. And we know the estimator for the support rate is equals 0.4. And we want to figure out the 95% symmetric confidence interval. For this one, we want to recognize that we have a sample of Bernoulli distributions. It's a Bernoulli distribution because the poll just asks people whether you support or not support the president. So if the support xi equals 1 means support, xi equals 0 means not support. And the support rate among the population is P. X and bar is an estimator for that P. Given the sample we calculated, this X and bar equals 0.4. Now, because this is a sample from Bernoulli distribution, we know sigma square equals P times 1 minus P. It's the variance of xi. And therefore, the sigma, an estimator for the sigma will be X and bar, which is an estimator of P times 1 minus X and bar. So that would be 0.4 times 0.6, 0.24. Using all this information, we can come up with a symmetric confidence interval. We know for this case, root n dn over sigma hat will be equal to 1.96, which is the z-score corresponding to the 95% confidence level. And therefore, dn will be equal to 1.96 times 0.24, square root of 0.24 divided by 10, which is square root n. So that is the dn, and the confidence interval of this confidence level will be L and UN will be X and bar, which is 0.4, minus dn to 0.4 plus dn. So that will be the confidence interval for this data set. So I want to stress one last point. I want to talk about one last point. That is the length of a symmetric confidence interval. The length of the symmetric confidence interval Suppose the confidence interval is of the general confidence level 1 minus alpha. Then the length of the confidence interval will be 2 times the dn corresponding to that confidence level. And that dn is sigma n hat divided by root n times the z-score. So the length is 2 times that. This length, sometimes you might be asked to choose the sample size to get you the desired length. The length is also called half of the length. The dn is also called the margin of error. So that's the dn is also called the margin of error for the confidence interval. Sometimes you might want to choose the sample size to get the desired margin of error. For example, in the poll case, presidential poll case, you get an estimate of 40%, and you might want to get a small margin of error. Let's say maybe you want it to be plus minus 2%. What that means is you want dn to be 2%. You want dn to be 2%. What do you have to your disposal to make that happen? You don't actually have any control over the z-score. The z-score is given by your confidence level. If you want to maintain a certain confidence level, that is a given number. You don't have much control over sigma hat either, because sigma hat will be close to sigma, which is the population standard deviation. And population standard deviation depends on the population. You cannot choose the population if you don't want to change the problem that you're studying. You don't have much control over these parts. What you do have control over is the sample size. So you can choose your sample size to get your desired margin of error. You can, if you want the margin of error to be a particular C, then you want to choose your sample size to satisfy this to be C. And therefore, the sample size should be sigma hat squared, z alpha over 2 squared over c squared. You want to choose the sample size to be this in order to get your desired margin of error, let's say C. And of course, there is the complication of how do you, which estimator to use for the population variance. That can come from historical data, or it can come from a preliminary sample that is maybe not as big as you want. So that can come from some other source. Once you get a guess of the population variance, you can choose your sample size to control the margin of error. All right, so that is it for this video.